Continuing with our topic of electrophilic aromatic substitution, this video we are discussing sulfonation and Friedel-Pabst alkylation and acylation. Sulfonation is actually one of the key reactions in several of the synthesis we will be doing with benzene. Take a benzene, react it with what is called as fuming sulfuric acid to form a sulfonated benzene. And what is fuming sulfuric acid? It is sulfuric acid with SO3 in it. That's an equilibrium in this form. And if you add excess SO3 to sulfuric acid, you can actually push this equilibrium to the forward direction. And that is what is called as the fuming sulfuric acid. So when benzene reacts with fuming sulfuric acid, you can form this substituted benzene here. Okay. Again, remember, benzene does not show addition reactions. It would rather show substitution reactions where the proton here is, or the hydrogen is substituted by different electrophiles. Okay. So SO3 is actually my electrophile here. It is electron deficient at the sulfur atom. As a result of which, benzene can react with this sulfur in this manner. Okay, again it's a nucleophile attack. So benzene's one of the pi bonds opens up, so reacts with at this point with sulfur, pushes the electrons to the oxygen. We draw this oxygen here. Keep the lone pairs. All right. So what do we get is a benzene or a sigma complex. Now we have a sigma complex, as we saw in the previous reactions of nitration and halogenation. Now we have an oxygen atom with a negative charge, and this benzene ring now gets a positive charge. Okay, so this is my sigma complex, and as you recall, this sigma complex is stabilized by resonance, so you get to move the positive charge all around the ring. So again, identify the three atoms at which the positive charge can move. This one. So we have this bond intact, right? Because we are going to move it over here. So this bond, we leave it intact. Double bond moves here, and then the positive charge, the sulfur bonding is two of the oxygen atoms, it is double bonded, and then with the other it is single bonded. Okay, and now where will the positive charge move? We have to consider these three atoms on which the delocalization of electrons would happen. So we can move this pair of electrons here, right? So this bond remains intact. Now the bond is moved, pi bond moves here, and the positive charge comes to this point. And now again, leave the bonds to the sulfur as before, with one of the oxygen atoms single bonded with a negative charge. Okay. So this is the reason why the sigma complex is formed, because it can be stabilized by resonance. Okay. But in the next step, so this was step one, and now the next step is where the aromaticity is regained. So, but before that, we have to show that the proton is being removed. So I'll pick one of the sigma complexes from here. Right, and again, remember, as in the previous cases, we are going to keep showing that proton, right, the one that will be removed in the end by the base. So it's good to keep drawing the proton to show how the base will come and remove it in an acid-base reaction. Okay, so I will still keep drawing the protons. Okay. Pick one of the sigma complexes. Keep the positive charge here. Right. Now, which one would be our base? Base can be the HSO4, or it can B1 HSO3, HSO4 minus when we remove the proton from here, right? So that HSO4 minus can be your base. Remove the proton, put the electrons back here to give back the aromaticity on the benzene ring. Okay, so we can put this back. S double bond O, and it is an ion here, but actually this ion, an ion can take a proton from sulfuric acid. It's again an acid-base reaction, and that's how we get the sulfonated benzene. So proton from here, put these electrons here, and finally you get the substituted benzene or the sulfonated benzene. So you can now write it as SO3H. Correct? See, S, 3 O's, and then it takes the proton from here. Okay, so that's how the mechanism of sulfonation is understood. Formation of the sigma complex. First, attack of the benzene ring onto the sulfur, formation of the sigma complex, resonance stabilization of the sigma complex, and finally the base, which is HSO4 minus, right? From here you can see that H2SO4 can be written as dissociating into HSO4 minus and H3O plus, correct? So that HSO4 minus is my base, which takes the proton, and finally you get your substituted benzene. All right. Okay. Now let's look at the another reaction, which is Friedel-Crafts alkylation. Okay. In Friedel-Crafts alkylation, benzene reacts with acid chlorides in presence of, not acid chlorides, alkyl chlorides in presence of a Lewis acid to give substituted benzene. Again, an alkyl group is what is substituting in the place of hydrogen. Okay, so let's write down the overall reaction again. Benzene, so what we need is a alkyl chloride. So for that we can use an example, say CH3Cl. This is an example of a primary alkyl halide. It could be a bromide too. Okay, we can use any alkyl halide. Well, actually, we cannot use any alkyl halide. There are some limitations, but this is an example I'm using with methyl chloride. In presence of Lewis acid, AlCl3, the product is where the proton again is substituted with a CH3. Mechanism wise, very similar to what we have seen before. First step, formation of the electrophile. So what electrophile will be formed here? Let's check. So CH3Cl reacting with, first step, Lewis acid. So aluminum chloride, if you recall from my previous video, we had said that aluminum chloride is a Lewis acid. It has only 6 electrons in its octet, so it's short of its 8 electron octet. So it can accept a pair of electrons to give this complex where we have CH3, Cl, Al, Cl3. Okay. However, chlorine is now positively charged because it has used up its pair of electrons to form a bond with aluminum. Okay, so chlorine is a electronegative element, not like to keep the positive charge, so it has a high tendency to pull the electrons from this bond, okay, which gives me the electrophile. So here is my electrophile. It's actually a carbocation, methyl carbocation, and the side product is AlCl4 minus. Okay, So here is my electrophile in the Friedel-Crafts alkylation reaction. So the next step, so this was step 1, formation of electrophile. Step 2 is reaction of the electrophile with the benzene. So as you see, the second step is pretty repetitive as we saw in the previous examples. Keep drawing the proton, react it with the electrophile now, which is my CH3 plus, the carbocation, methyl carbocation. Benzene opens up, pi bond, one of the pi bonds opens up, attaches to the carbon atom here, you get the sigma complex. These two bonds here, CH3, positive charge over here, and make sure you're able to draw the resonance structures to show the stabilization of the sigma complex. Moment of positive charge around the ring. Keep drawing the hydrogen because we will be removing the hydrogen in the last step. One more resonance structure where the positive charge moves to this carbon atom here. Keep the CH3 and the proton. So these are the 3 resonance structures for the sigma complex. Step 3 for the mechanism. Pick any of your sigma complex from above, just using the first one, and show the acid-base reaction where the proton is removed and the aromaticity is regained. How do we remove the proton? This aluminum AlCl4 minus is going to pull the proton here, put back the electrons onto the ring, and we get the substituted benzene, which is a alkylated benzene. Okay, so here, if you recall, this is actually toluene, right? So one method of synthesizing toluene would be benzene reacting with a methyl chloride or a methyl bromide. Okay, so this is a useful reaction for alkylation. However, Friedel-Crafts alkylation actually has some limitations. Okay, and one limitation is, so let's talk about the limitations of Friedel-Crafts reaction. Because all alkyl halides will not work for this reaction, and the ones which do not work are not good reagents for Friedel-Crafts alkylation are aryl halides and vinyl halides. They are not good halides to react with benzene for alkylation or for adding any aryl group or a alkyl group. Okay, so how do we draw that? So this is an aryl halide. This will be an example of an aryl halide, and a vinyl halide would be something like this. Okay, so these are examples of aryl and vinyl halide. And the reason they don't work is because the carbocation that is formed from the vinyl halides and aryl halides are highly unstable. So carbocations are highly unstable. So that's the reason we do not use these electrophiles formed from these for the Friedel-Crafts reactions. So we can say they are unreactive halides. This was one limitation. Second limitation is that if you have electron withdrawing groups, so electron withdrawing groups, like SO3H or NO2, cyanides. Okay. If the presence of these on the benzene ring will make the reaction slower when we are doing a Friedel-Crafts reaction. Okay, so these are electron withdrawing groups. They make the benzene ring less prone to reacting with any of these carbocations. Okay, so presence of electron withdrawing groups slows down a Friedel-Crafts alkylation reaction. Sometimes it does not even work out. So we have to avoid using benzene rings with these groups present on it when we are doing Friedel-Crafts alkylation. Third limitation, we can say electron withdrawing groups slow down Friedel-Crafts alkylation. Another limitation is that polyalkylation can happen. That means sometimes when you react with an alkyl halide, so for example, you treat it with CH3Cl and AlCl3, these are the reagents you need to for alkylation. You not only get a mono-substituted benzene ring, but you can also get poly-substituted benzene rings. That means, say, you can also have another CH3 group substituted at this position. Okay, so this is called as polyalkylation. And then finally, the fourth and major limitation is that rearrangements can happen for the carbocation. So if you have, say, a probability of hydride shift where a primary carbocation can rearrange to a more stable secondary or tertiary carbocation, then we can also get rearranged products in our reaction mixture. So let's look at an example of that. Okay. So the fourth limitation is rearrangement. Rearrangement of carbocations. Okay, so one good example would be when I am trying to react the benzene with, say, CH3, CH2, Cl, this is an alkyl halide, and AlCl3 as my Lewis acid. So the expected product is that I would like the, oops, actually I made it CH3, CH2, CH2Cl. Okay, so I'm going to take this alkyl halide with 3 carbon atoms. So expected product is where this carbon atom, let's put a color here, okay, this carbon atom is the one that's going to be attached to the benzene ring. And we get CH2, CH2, CH3, right? So this alkyl group should be attached to the benzene ring like this. However, this is not what we get. The actual product, so actual product is a rearranged product where instead of formation of this, we get an isopropyl benzene. Okay, so instead of the propyl benzene, which is expected, I do not get that, but I actually get this product. And the reason is, maybe we can understand it through the mechanism. So again, remember, step 1 in the mechanism is formation of the carbocation, right? Or the electrophile. So here, I'm not going to write the whole step because we did it before. So the electrophile that we are expecting to get is this one, right? Where here is my carbon with the positive charge, right? This is my carbocation that I form by when I react with this propyl chloride with AlCl3. However, if you look, this is a primary carbocation. It's a primary carbocation. If you recall, there can be a hydride shift. Okay, so we can have a rearrangement reaction where the primary carbocation can change or rearrange itself to a, we can call this hydride shift, to a secondary carbocation by moving one of the hydrogens from here to here. So we get CH3, okay, because one of the hydrogens moves from here to here, and then the positive charge is actually on this carbon atom. Okay, so when the benzene reacts, it's going to attach itself to the carbocation that's formed here, which is a secondary carbocation. See, it's a secondary carbocation. So it will attach itself to this one, this carbon atom, rather than this primary carbon atom. Right? So we can redraw that. CH3, CH3 plus, right? So see, now it's going to attach itself to this carbon atom to form the sigma complex again, right? So here we can use the color. It's attaching it to this purple carbon. So that's where it is attaching. So we get the isopropyl. Okay, so we have the sigma complex. Draw that. Okay, and I'm not going to draw the resonance structures because I think you understand now. And then finally, it gives the product, which is an isopropyl benzene. My carbon atom, the purple carbon atom is the one that's over here. So this is actually a limitation for the Friedel-Crafts alkylation because this is what I wanted, right? I'm expecting to form this product. However, this is what I get as my actual product. So there is a way around it, and we'll look at that in the next reaction. But I would like you all to make sure that you understand the limitations of Friedel-Crafts alkylation, 4 of them. One is that you cannot use aryl halides or vinyl halides to form the carbocations because their carbocations are highly unstable. Electron withdrawing groups like SO3H, NO2, CN, etc., they deactivate the ring, or they kind of render the ring, benzene ring, less nucleophilic, as a result of which Friedel-Crafts alkylation either slows down or sometimes it does not happen. And polyalkylation is also a problem sometimes because once an alkyl group is placed on the benzene ring, then it can induce the attachment of other alkyl groups in the ring, as a result of which we might get polyalkylation. Okay? And then the final limitation was that the carbocations can rearrange if there is a possibility of a more stable carbocation to be formed. Okay? So this, like I said, this last limitation we can get over that by doing a Friedel-Crafts acylation so that we can get the expected product instead of the rearranged product. Okay, and so that's what we are going to see in the next and the final reaction for electrophilic aromatic substitution reactions of benzene. Okay, so the final reaction is Friedel-Crafts acylation. What is an acyl group? So acyl group is, say for example this one, this would be an acyl group, this part. Okay, so we are introducing an acyl group onto the benzene ring. Okay, so let's write down the overall reaction again. Benzene, when it reacts with a acyl chloride or bromide, okay, so you can use an acyl chloride or bromide. Okay. And again, remember, this is an R group. It's not necessary to have 2 carbon atoms the way I showed. You can even have 1 carbon atom, 3 carbon atoms, it doesn't matter, as long as you have an R, CO, and a halogen. Generally it is a chloride or a bromide. So this is your acyl group. Okay, so your R can vary. So in this case, I'm taking a 3 carbon atom total in my acyl group. So we have a chloride here. Again, this reaction takes place in the presence of a Lewis acid, AlCl3. Okay. And what we end up in getting is substituted benzene, a ketone. Right? So I would put a color here just to highlight that this is the carbon atom, which is the point of attachment. Okay, not any of these. So the carbon bearing the oxygen, or the double bonded oxygen, is the point of attachment. Okay, here my electrophile is formed in a similar way as we did with the previous steps. So let's look at that. Here is my acyl chloride reacting with aluminum chloride. Step must be familiar to you now. Okay, so chloride is the Lewis base, this is the Lewis acid, and you get the complex where chloride is now attached to this aluminum. Okay, getting a positive charge, but really pulls this electron towards itself, so that we get our electrophile, which is my carbonyl carbon. Okay, so this carbon is my electrophile. So I can again put the color back over there. Here, this is the carbon that has got the positive charge. So I have the electrophile here. The another feature of this electrophile is that it can undergo resonance. So it's stabilized by resonance in this manner. So you can actually use this pair of electrons from oxygen, and you can form a triple bond to the oxygen, but it will get a positive charge, right? Not one of the major contributors to the resonance, because oxygen has a positive charge, but still this acyl ion is, we call it as an acylium ion. Okay, ACYLIUM, acylium ion, is stabilized by resonance. All right. The other feature of this acylium ion is that it does not undergo rearrangement. No rearrangement in this case. Okay, unlike in the case of a alkyl carbocation, where depending upon whether you have a secondary or a tertiary position available, rearrangements can happen. But in this case, there is no rearrangement. That is why we can safely perform the reaction with any number of carbon atoms and form a substituted benzene in this case. All right, so let's finish up this reaction. So this was step 1, formation of the electrophile, which is this one, my acylium ion. Okay, step 2 is when benzene reacts with the acylium ion, that's a carbon atom onto which the benzene is attacking. I'm sorry, we don't have that arrow here because it's a positive charge, right? So sorry. Then we have formation of the product. Okay, I'm not drawing the whole resonance structures and the sigma complex, but I think you now know, as in the previous reaction, this will open up and it will form a sigma complex, stabilized, and then finally the proton will be removed by the AlCl4 minus, right? The AlCl4 which was formed in this step, see, this one, it's the one that's going to remove the proton, and you get the final substituted benzene. Alright, so now we have the molecule here. The way we can change this into a propylbenzene, because that was our problem, right? Remember, let's go back to the previous page. See, this is what we wanted, right? A propylbenzene. So we said that we can use Friedel-Crafts acylation to form propylbenzene. Right now, it's not a propylbenzene. We still have the ketone group here, but we can actually do a reduction reaction, which is called as Clemenson's reduction. So if you form this first, then you can take this molecule and react it with zinc in acidic conditions, or reduce it under acidic conditions, zinc amalgam. Okay, whenever we have a metal with a mercury, we call that as a amalgam, and we use the zinc amalgam in acidic condition, HCl, and actually you can remove the or reduce the ketone group and form the propylbenzene now. It's a very useful method to avoid any rearrangements. So you can take benzene, convert it into use the acyl chloride to form this ketone, and then finally do the Clemenson's reduction. Okay, this reaction, the final reaction, is called Clemenson's reduction. That's how you can get the propylbenzene. All right, so this is something that's pretty useful, especially when we are doing synthesis. You can keep these two reactions in mind, that when to do Friedel-Crafts alkylation, and in case rearrangements are happening when we are doing a Friedel-Crafts alkylation, we can use this pathway of acylation, where you first convert the benzene into a put the acyl group on the benzene first, and then reduce the acyl group with zinc in amalgam in HCl to form the respective alkylated benzene. Okay, all right. So this ends the few reactions of benzene. Let me quickly summarize, and then more we will talk about in the other video. Okay, so as a summary, we can say that if you have benzene for mono-substitution reactions. Mono-substitution means if you want to put one substituent, then these are the reactions which we have studied. Okay? One, if you take chlorine in presence of AlCl3, okay, chlorine and AlCl3, you can put a chlorine onto the benzene, halogenation, that was a halogenation. If you react it with HNO3 in presence of H2SO4, both strong acids, then you end up in a nitro group substituted on benzene. If you use fuming sulfuric acid, H2SO4, you can get sulfonated benzene, okay, SO3H. If you use alkyl halides like CH3Cl in presence of AlCl3, okay, you can get alkyl groups substituted on benzene. Or if you use acyl halides like CH3CO Cl, then you can put the acyl group onto benzene. Again, don't forget the Lewis acid, AlCl3. So you can install the acyl group in benzene. Okay, and then one further reaction which we looked here was that if you use zinc in presence of mercury in HCl, you can actually reduce this double bond and change it into an alkane, okay, or an alkyl group. Oh, one more reaction which I forgot to tell you is that if you have a nitrobenzene, you can again you either use zinc or Fe in acidic medium, and you can reduce this to an amine group. Okay, here again I'm not expecting you to know the mechanism at this point. Just for synthesis purposes, it's a useful reaction that when how do you put an NH2 group on a benzene, right? This is called as aniline. So you can actually form aniline from benzene, kind of a synthesis steps. You take benzene, do the nitration to put the nitro group over here, and then use this reducing conditions with zinc or iron in acidic medium to form the NH or reduce the NO2 to NH2. Okay, so this is kind of a summary of our electrophilic aromatic substitution reactions of benzene. In the next video, we will talk about directing effect. That means if you want to put another group on a mono-substituted benzene, then how will we decide where that group would go? Would it go to the ortho position, to the para position, or to the meta position, etc.?